and fine. Yes, this is about red black trees. Red black trees. Already we discussed in the last class red black trees. After AVL, we also have the red black trees, a balancing binary stress tree. I told you that. So we discussed yesterday previous section, that is about red black trees. So what are the rules are there in the red black trees? We discussed which is the red black tree, which is not red black trees. We discussed, and also insertion in the red black trees. The rules I told you that, and example also we discussed, and insertion in different positions. So what are the rules we need to follow while inserting? How to change the color and how we are rotating the subtrees. We discussed, and now and when compared with AVL trees, I already told you that similar to the AVL tree only, but sometimes AVL trees are slower in section and removal. Okay, so when compared with red black trees, so that's why. Another self-balancing binary search tree is Splay tree. In this class, we are going to discuss about the Splay trees. Okay, uh, Splay trees. Splay trees was invented by the Daniel Slater and Robert Arjan. A splay tree is a self-balancing binary search tree. One property is the additional property. The reasons recently assessed elements can be reassessed fast. Recently assessed element can be reassessed fast. Okay, so that is about still all are adding. The split, yes. Simple idea it is behind this one is simple idea behind this one uh, is that if an element is assessed, it is likely that it will be assessed. So and then for many non-uniform sequence of operations, for various sequence of operations, play trees perform better than the other search trees. Yes, and so when we assign a node, splaying is performed on the node to move it to the root. Splaying means spreading. We are spreading. If you perform any particular node, splaying on the particular node, that node n, for example, node n, so can be placed as in the root. How we are doing means we are following the steps. Three types of steps are there: jig step and jig step, and third one is jig jag step. Okay, if you see the jig step, for example, is, so suppose this is the node n, okay, which is not the root. Okay, I make it as a n as a root node. Okay, whereas a p as a right subtree, right child to n. Okay, how? By rotating. By rotating means I need to make the move the upper part from for left rotation. That means from left to right we are rotating. So n will come as a parent and p as the child. Here see here whatever the t1 as a t1 as a left subtree to n, and whereas here 2 to t2 as a add as a child left child to p. Okay, so this is the thing. This step I can say it as a jig step. This step is I can say it as a jig step. So how we when we perform we'll see later, but we need to know when splaying is performed, one of the step is jig step. So this is the way happen. And next one is jig step. Next one is jig step. Here jig operation is performed when p is not the root. Yes, besides n and p are either both right or left child of their parents. Okay, so that is you see this p already told you we not a root node, and whereas a child to p n is there. So I want to apply the splaying on n again n here. This time n is this side. Suppose in this case, as a child to the p, here p is not the parent. Okay, let's see now. G is the parent. G is the root node. Okay, p is not root node. G is the root node. Okay, and p is a parent to n. So in this case, I want to make n as a root node. So I need to replace g with n. How I can do this? So simply see, same thing from left to right rotations. It is similar like double rotations. Okay, see here, after moving up n, this first of all, as a right child g to the p happen. Again, I will do the rotation to the right side. At this time, here is giving direct step. Okay, n as a parent and the right child as a p, and g as a for p, g is the right child. Yes, here you see this is the T1 always will be the left subtree for n. Okay, when even n reaches as a parent, whereas T2 become as a left child to p, and whereas T3 become as a left child to g. Okay, so this is the thing. So this is the thing. Yes, this is the thing. And next one, I will show you that one thing. Yes, I'll show you that. This again. Suppose if n is here, if is n is here as a right child to the p. Okay, I want to apply this playing on n. Okay, so after applying this playing on n will be the parent. Okay, see what happened. Two times I will do to the left side rotation. Okay, for the right to the left side I'm moving. Okay, so two times after two times I done, then I will get this form. So n will become as the parent of root node and parent to p, and p is a parent to g like this. And for g, t1 and t2 as the childs to g, and whereas t3 will become as a right child to p. Okay, and p have the right child. T4 this not change. This three these are changing. This one is not the changing. Okay, and so this is the jig step. In jig steps, there are two cases are there. Whenever left side leftmost in the left side, whenever n is there, where p is a parent to n. So in this case, like this, I can change, or if it is right side, n is in the right side to the p. Okay, in this case, I can make n as like this. Okay, these two are nothing but jig steps, jig steps. Okay, so this is about jig steps. Next one is the zigzag step. Okay, this sometimes in this situation, I applied the zigzag operation performed when p is not the root. In addition to this, n is the right child of p and p is the left child of g. Okay, let's see now. N is the right child of p and p is the left child of g. Yes, and p is not the root. Yes. In this case, what happened now? Uh, right rotation means from right to left I'm rotating, and I make it as n as a parent to p. Okay, p as a left child. Okay, this is the thing happen in this case. During this case, t2 is become as a right child to p. Okay, so this thing happened two times. Double rotation will take place, similar like AVL. Okay, so after this I want to make n as a root node. Okay, because I'm performing splaying on n. So I need left rotation means from left to right I'm rotating. Okay, so if I'm moving like this means now n will become root node, and whereas g as a right child, and T3 and T4 are the children to G, and whereas T1, T2 as a children to P. Okay, and have left and right as a P and G children's. Okay, so this is zigzag step in this case. Okay, let's see now insertion. This operations, splay trees insertion operations. Actually, so we have to know briefly how to know about the insertion operation also in the splaying. Okay, insertion search we'll discuss. Okay, as per syllabus, just splaying what is the splay trees is enough. But anyhow, so we are discussing splay trees. So briefly we'll discuss about insertion and search at least. Okay, so let's see how I'm performing insert a new node in the splay tree. Suppose first of all, to insert a new node new node in the splay tree. Okay, so I need to search n in the splay tree whether the n node is already is there or not. If it is successful, play at the node n. Okay, insert a new node n. Okay, in the insert operation also, if the new node already it is there, suppose the element is already is there, means I can apply the splaying at the node n. Or otherwise, if the n node is not present in the splay tree, in this case, the in this place I can where I need to place the new node. So based on the rules we follow, that means binary history rule only here also apply. So an appropriate position replace the null pointer and attach to a new node n. Okay, by searching only from root node to that particular path, replace that null pointer and attach the new node n, and after that I apply the play the tree at n. Okay, suppose there are two cases are there. If the already element is there, no need to insert. For that element n, I need to apply splay. If the element is not there, second case, so I need to search that path and attach the n and apply the splaying at that node n. Okay, so this is, so how I'm doing, this is the example. You see here, I want to insert the 81, whether the 81 is present or not. Yes, it is not there. This is a binary search tree only. Okay, as like AVL tree, it is also binary search tree only. Let's see now. Yes, 54. So 81 is greater than, that's why I need to move to the, I need to search 81 right side. Still 81 is greater than 63. So again, I need to go to the right side. 81 still less than 90. So I need to go to the left side where still 81 is not present. So in this case, that 81 should be attached as a right child. Okay, first of all, as binary history, I need to attach here also like that. Yes, after attaching, so when you are inserting splaying that node 81, 81 is a n. I need to apply the splaying. Okay, so it is like I already told you that zigzag steps I can apply. So what happened in this similar like AVL trace? Yes. So I need to move 81 because I want to make 81 as a root node. Okay, what I will do? I need to move 81 here, zigzag step. 81 will come here, and 90 as a right child, and 99 as again the rightmost child. Okay, to 90. Yes, 72 as a similar in zigzag steps. Nothing. So 81 come here, 90 as come as a right child. Okay, so we get, still it is not completed because this is the one step. 81 I want to make it as a, if I'm applying splaying on 81 means I need to move this 81 to here. So two times I will apply the rotation. I think the two times I need to apply the rotations. You see now what happened. 81 come here. So yes, for 81, 63 is the child. Again need to go to the top 81. So 81, for 81 may make as a, suppose I'm moving this side. I'm moving this side. In this case, when I'm moving this part will go as a left subtree, represent as a left subtree. See here how after moving up. See here. So for 63, the 72 will become as a right child. Okay, right child. And remaining is not almost is not changed. Remaining is not changed. Only 72 attached as a right child to 63. So when I make that 81 as a uh, parent node. Okay, so yes, in this case, yes, what I have done actually, yes, mm. In this case, in this example, I applied the zigzag steps in this zigzag step, and here I applied the zigzag step. So in while inserting 81, I need to apply the splaying on. After inserting 81, I apply the splaying at 81. So for that, I applied the two steps. One is the zigzag step here, and after that, I will apply the zigzag step. So finally, 81 will become the root node. Okay, so this when we are inserting 81, like that only the same process will happen. Suppose search operation. Okay, suppose I already told you that if the search is unsuccessful, yes, searching operation I'm telling. searching. This is not inserting. Inserting means this is the inserting. Okay. Okay. In the search operation, when the search is unsuccessful, we need to reach to that path. We need to reach to that path. See this here. Suppose I want to search 81. Okay, in this tree. So, say 81 is greater than. Let's see this example. 81 is greater than 54. Yes, this side I will search. Again, 81 is greater than 63. This side I will search. Again, 81 is less than 90. Same as previous example it is. Still here I'm searching. 81 is greater than 72. But right side null pointer for 72, right pointer is null. So here 81. So that means search is unsuccessful. So in this case, if the searching is, even if you say searching operation also 81 is not present, meaning the in binary search tree, we say simply say it as a 81 is not found. Yes, we can display like that. But in here, okay, not only that one, I need to apply the splaying on 72 also. Splaying, that means I want to make 72 as a root node. Okay, but in binary systems, if the element is there, then I just simply display the element is found, otherwise not found. But here, not only that one, I need to apply the splaying at node n. This 72 will become the node n. So same process we apply here. First I will apply the zigzag step. Zigzag step, yes. Yes, after applying zigzag step, I will get the 72, and after that I will apply the jig step, I think. Yes, you'll see the jig step. Yes, jig. What step? Jig step. Okay. Yes. Similar like the jig step, left side, right side also. Okay. So here. So after that, I will make 72 as a parent node. So I need to move to the rotation. Okay, right rotation means right to left. So after moving up 72 as a parent, whereas right, left child as 54 and 90 as a right child. But here 62 attached as a right child to 54. So like this is happening. So even searching operation also, if it is fails means, if it is fail, if it is fail also, we need to apply the that splaying on that where I stopped the path, that is 72. Even searching is successful, 81 is also there, means I need to apply splaying on 81. If the 81 is present, again I need to apply the splaying. But here 81 is not present. In this case, the last node where we stopped the searching from root node to last node, there I can apply the splaying. After applying splaying, 72 will become here. So this is enough. So this is about it. So this is searching and insertion operation. This is happening in searching and insertion operation. Okay. Yes. Even even here also same thing. Ah, fine. Okay. Inserting, no problem. Okay. Searching, insert. This is enough. This, as per the syllabus, will only introduction. So, but anyhow, I discussed how this playing performed. Uh, the playing performed when you are inserting or when you are searching. Okay. There are three steps: jig step, um, jig step, and zigzag steps. Okay, based depends upon we apply the appropriate steps. Okay, to make the root node n as a root. Okay, so this is, and now, so this is enough. So if you in a case study, if you want, then I will discuss delete operation also about splaying. As per syllabus, we covered a lot of things, that is about red black trees and splay trees also. And let's see the next main topic uh, in this balanced binary search trees, binary search trees, that is M-based search trees. Why we are discussing this M-based search trees? In this section, I will discuss about M-based search trees. M-based search trees. What is that M-based search trees? By following the M-based search trees, it is extended to the another type of search trees, that is the B trees and B plus trees also. We'll discuss later. That is, at least we need to discuss this one, M-based search trees. Okay, let's see. AVL red black trees are unable to take advantage of this large unit in which data is moved from slow memory to faster memory. So still AVL performs searching operation better, but it is unable to take the large bulk of data from slow memory to fast memory. It is so that is one problem is there. If you apply AVL tree, red black trees, even Splay trees also here not mentioned. Okay, even since the node size is few bytes only. For example, let's see AVL tree. Suppose I am taking AVL tree with 1 lakh elements. Its height may be as much as 1 point floor. I think seal 1.44 log n plus 2 to the base 2, okay, closing the floor, which is almost equal to 28. That means height of the tree is 28. So to search any this tree for a particular for an element with a specific key, we must access those nodes that are on search path from the root to the node that contain the desired element. So this path may contain 28 nodes. In the worst case it is okay, 28 nodes I want to search from a root node to the node with the desired element that contain the desired element. If each of these 28 node lies in a different memory location, for example physical means logically, so it allocate the different memory location each node. So total of 28 memory accesses we require, and 28 compares are made in the worst case. In the worst case this is happening. Most of here the problem is the most of the search time is spent on memory access only while searching, okay, or insert or delete operations. In the worst case, most of the time is spending memory access. I want to decrease that memory. To improve this performance, what I need to do, I need to must decrease the number of memory access. Number of memory access to decrease means I need to compulsory reduce the height of the tree. Okay, we must reduce since the number of memory access is closely tied to the height of the search tree. So I need to reduce this. So that's why we are discussing this MWay search trees. So we must use search trees whose degree is more than 2. This is the importance of this MWay search trees. Okay. So because of searching operations by using suppose AVL trees or red black trees, okay. So in the worst case, the memory access is more. So I want to reduce that one. Okay. So that's why I'm discussing this search trees whose degree is more than 2. Okay. So this is now let's see what are the rules are there. So it is little bit try to understand this one. Some rules are there. Try to understand what are the rules it is. Okay. Yes, MWay search trees. So M-based search trees maybe contain yes, M-based search trees maybe contain T maybe an empty tree or maybe a non-empty tree. If it is a non-empty tree T, then following properties should be satisfied. One of the properties for some integer M, known as order of the tree. Order of the tree means degree of the node, that particular node, root node, degree of the root node. Say M. Yeah, order of the tree. So it is not at most. Yes. Um, it is not the exactly m should not less than or equal to m. Yes. Each node of has at most m child nodes. Has at most m child nodes. Each node has at most means uh, at maximum 0 or 1 or at most are equal to m and so on equal to m like that. 0 to m nodes child nodes should be there, not greater than m plus 1. So a node may be represented as, each node I can represent it as, see here, what is this, a naught. So, and also key value, first key value and a1, second key value a2, and k m minus 1 and a m minus 1. Okay, where ki, ki is nothing but 1 less than equal to I less than equal to m minus 1. So, at most m less than 1, m minus 1 keys and KIs and AI also. M minus 1. M minus 1 I want. What is this K? This is nothing but K, keys. Nothing is key values. Okay. And what is AI? AI nothing but pointers. AI are the pointers to the subtree of the T. Okay. Let's see what is this terminology. We'll see this one. Later we'll see. First of all, that is the first rule. Second rule, if the node has K child nodes, Okay, if the node has k child nodes, okay, where k less than or equal to m, okay, then the node can have only k minus 1 keys. That particular node have only k minus 1 keys, okay, which having the k child. That is the rule. And then, while we are inserting, we'll understand and contain the node such that ki less than ki plus 1. You see this one also. Okay. Yes. So this is the another rule. We'll see that. And second, uh, for a node, third condition, third property is for a node. This is the for a particular node. These are the values. All the key values in subtree pointed to by ai, pointed to by ai less than. In the same for a node, the left suppose subtrees are there. We have for subtrees key values. Key values is pointed to by ai should be less than or equal or less than the key ki plus 1, ki plus 1. Okay. uh, in the subtrees, suppose if maybe left subtree, I think in the left subtree the child nodes have the key values. That key values should be less than the ki plus 1. Okay, and all the key values in the subtree, that is subtree for that particular node right side, should be greater than km plus 1, km plus 1. Okay, km plus 1. So here less than means less than k1, so this side left side, yes, okay, and greater than uh, km minus 1, okay, greater than this side right subtree, okay, like that. You see right side as a right child. Okay, you see that is the third case. Fourth case, each of the subtree ai are also m way search trees. These are the four rules. Okay, these are the four rules. So in the next section, this section is going to close. Now again I will start the next section. In the next section we will discuss about m-way search tree with example. Let's see, this is the one. Okay, so yes, fine. Yes, this is about in this section this is about the m-way search trees, okay, and splay trees. Okay, in the next section we'll discuss with example.